Welcome to the second SkelForm tutorial, where we will be going over inverse kinematics. I will continue reusing Chibington from the first tutorial, but of course, you can use any character. Alright, continuing off from the second tutorial, where we added the inverse kinematics, let's go to the hat here. Right now, the hat is a little boring. It's not really deformable, we can't really shape it or mold it, and normally that's what hats are, right? Since they're clothes, we would want to be able to mold them around, maybe make them sway a little. So the way that we would do that is on the right side here, in the mesh deformation section, let's click on edit vertices. You can also click V on the keyboard, and this will now show a green square around the hat, but it will also show two triangles. These two triangles represent the texture itself. So let's say, for example, you were to hold left click and you were to drag the triangle. You can see that it also drags the entire texture and it also deforms the texture. Once again, that's because the texture itself is made up of these triangles. So for example, if we were to drag one of these singular points, it would also move just that one point. We can also move the bottom right point to change the bottom right triangle, or move the top left to change the top left triangle. Now let me reset the texture by clicking on reset on the right side. But the fun part is what would happen if we were to click trace. And what this does is that it will, as accurately as it could, trace the entire texture so that the mesh more accurately represents it. So you can see now that the triangles that form the texture look more like the hat itself. Now, of course, this is quite a bit of vertices. It's not really needed. For example, we could remove some of these. If you right click on a vertex, it will remove it. So we could do a bit of cleanup like this, where we would slowly remove the vertices that are not needed. And we would, yeah, this should be already good enough. You can also press right click on a triangle to remove it entirely. So we would have a setup like this for a mesh. Or what you could also do, if you would prefer to mesh it manually, is you can press left click anywhere on the vertex, anywhere on the mesh, sorry, to add a new vertex. So what we can do is, oops, let me just go back to the, let me just go back to the hat. And what I'm going to do is I'm going to manually trace it by adding vertices myself. So just left click to add them. Oops. So you'll notice just now the bottom right vertex was automatically removed, and that's because if a triangle were to be formed here, you'll see that there's actually nothing in the triangle. There's not going to be any pixels or any texture data, so obviously that triangle would be useless. And so SkelForm will automatically remove any useless triangles for you. So if we do the same here, for example, you'll see that the top right triangle has also been removed, and we can keep going like this. And there we go. So this is my own manually traced hat. Of course, it's going to have the same result as if you traced and then you cleaned it up, but these are just the two ways that you can do it. Adjusting the vertices manually is good and all, but there is another way that we can modify them, which is to use another bone. So similar in concept to the target bones for inverse kinematics, let's create a new one, just an empty bone called bind. I'll put it somewhere here at the top. In fact, I'll probably make it a child of the hat. And what I'm going to do is I'm going to, on the right side here of the binds section, I'm going to create a new bind. And over here, we'll be allowed to set a bone. So I will set that to the bind bone over here. So now, if we were to select that bind again, when we enter the edit vertices mode, if we double click on any vertex, you will see that it will turn into a yellow color. And the yellow color indicates that this vertex is now part of the selected bind. So in this case, it's part of the first bind. And so what's going to happen if I were to move this bind bone now is you'll see that the vertices will also follow it around. And this also applies for rotations and scaling. Oops. There we go. So all of the transforms do apply to the vertices as well. Now let me just reset them actually. Let's add two more binds for the right and left side of the hat. So let's create a new bone. I'll call this one right bind and this one left bind. Position them just here and then go back to the hat itself. And then from here, we can actually create a new bind, set it to the right one. And so for this one, I think we can do these two vertices. And then we'll make another bind, which will be the left side. And then that one will be, I think these two would be good. So if we were to check it out now, seems good. Yeah, this one looks pretty decent. I think the vertices don't deform it too much. So from here, what we can do is we could start animating it. So one thing I want to mention is that we'll use the standing animation as an example. So one thing I want to mention is that you cannot animate the vertices individually. So for example, if you're on an animation right now, and if you were to move any of the vertices, it won't actually apply. So what you're actually supposed to do, and the way that you're actually supposed to animate a mesh, is by moving binds. And this is the main purpose of the binds. So for example, if I wanted to move the bone, move the hat slightly like this, maybe move the right bind as well, and the left bind. If you were to play the animation now, you can see that it is actually updating the mesh in real time. So if we were to put the binds back in place in the intermediate frame, and then maybe make them sway around like this, and then reset them again. If we play now, you can see that it is properly animating the mesh. And this is because the vertices themselves are being moved purely thanks to the binds. So once again, the top bind is going to be animating the top vertices, the right bind will be animating the right side vertices, and the left bind will be animating the left side vertices. So this is how you would actually animate a mesh. It's using binds, it's not using individual vertices. Another important detail about binds is each vertex in a bind, if you look at the right side, they all have a slider called a weight to them. So this will range from 0 all the way to 1. And what this does is the weight will determine how much the vertex is influenced by the bind. So in this case, if we were to set them to 0.5, just approximately, doesn't have to be exact, just as a demonstration. Now that the three vertices are around 0.5, which is 50%, if we were to move the top bind now, you can see that the vertices are not immediately following it. So the influence of the bind is only about half of the vertices. If I were to move the bind somewhere here, for example, and then I were to move them all the way here, you can see that the vertices are still not immediately all the way to the bind. Whereas if they were at 100% or 1.0, you can see that now they are actually around where the bind itself is. So this is basically how you can customize the vertices so that you can create more dynamic motion or more dynamic animation by making it so that not all vertices will have 100% influence of a particular bind. We can also do the same thing for the others. So for example, on the right side, we can make it just a little lighter on maybe the top side, but then the higher side will maybe stay at 1%. So if we do something like this, we can have the vertices act a bit more dynamically because now the bottom side of the hat will be influenced much further than the top side of the hat, since this is how we set up the weights. Or for example, on the left side, we can do something like the opposite, where the bottom side will have less of an influence. So if I set it to something like maybe 0.58, if I were to move the bind now, you can see that now it's the top part that has more influence than the bottom part. It does look kind of weird, but you do get the point. if you construct the mesh properly, then the effect should be less warped, but the point is that you can make the mesh more dynamic and more fluid if you adjust the vertex weights properly. But of course, this isn't necessary. You cannot actually just keep them at 100% at all times. This is just if you need that kind of flexibility. If you choose any bind in the right side section, right to the right side of the weights label, you'll see that there's a peculiar option called pathing. And you may be wondering what exactly this does. Pathing requires more than one bind, but it's basically like an imaginary line that's going around each bind and making it so that the vertices will follow along that imaginary line. You can use this for things like pipes, rubber hose limbs, vines in a forest, or anything similar like that. Just as a quick example for a mesh with pathing binds, here is an example with 4 binds. This is very similar to the diagram that was shown before. If we open the vertex editor, we can see here that there are 4 pairs of vertices, each with 2 vertices. And once again, just like in the diagram below, you can imagine that there's an invisible line going throughout the mesh. So it goes something like this in a curve. And if we go to each bind, we can see that the binding is actually set to true for all of them. So what exactly this does is, let's say that right now the limb is shaped like a curve. But let's say that I wanted to straighten it right now, just for demonstration purposes. Immediately you will see the effect that pathing has, because it's automatically adjusting the vertices so that they all face the way that they are supposed to. But let's say that I now wanted to make this limb bend down here. So what I would do is I would just position them like this. And there we go. And you can see that it still somewhat retains its shape as best as it can. Now, just as a demonstration for what it would look like without pathing, let me just disable it for all of them. And immediately you can see it's already starting to break. But let's say I wanted to straighten them. So let me make this straight. And immediately you can see that something isn't quite right. The mesh looks like it's being contorted and twisted like a piece of paper, because the vertices are not being adjusted based on where they are facing. So if you open the vertex editor, you can see that the meshes, you can see that the vertices are not in the same orientation. Whereas if we were to turn on the pathing, now if we turn on pathing now, of course we still need to fix the mesh as it is. So let me just quickly do that. It should be quite quick actually, since this is a relatively simple mesh. Just something like this. That should be it. And if we now move it, there we go, it's already fixed. Well, actually, it's a little misadjusted, but if you do adjust it properly exactly to where the binds are, you will get the same effect. Here's a demonstration of what this same limb would look like if it also had inverse kinematics. So at the very end, I also have the glove texture, and if we move this target around, you can see that it does work. And if we were to start bending the arm, you can see that although it is a little deformed as it keeps bending, it contorts a bit too much. You can see how the pathing actually works in general. It's more convincing of an arm, since you have the forearm side and then you have the front side. So this is how pathing is meant to be used. This is one of the uses for it actually. You can create more convincing arm meshes with using only one texture instead of needing to use multiple textures, because keep in mind all of this is being done with just this one singular mesh, and also with the glove as well, but that's not a mesh in itself. So if we try, let's see what happens if we were to disable pathing, just as a demonstration of why it's so useful. So now that with the pathing disabled, if we were to attempt to rotate, you can see that already it's being contorted too much and it's not actually respecting the rotations as they happen. if we were to maybe fix the vertices just quickly here, so assuming this is already a perfect mesh when it's straight, you can see that it's still going to contort when we start bending it because it's not respecting the pathing along the limb like this. You can see that it's wrapping around, it's twisting around kind of like a piece of paper. So this is where pathing becomes very useful. One last note I would like to give about meshes before finishing this tutorial off is this is an entirely optional feature. If you think that this is too complicated, or if you think that your armature would not benefit from using meshes, then of course you don't have to use it. This is more of a feature, this is more of an advanced feature that you would use if you prefer something like, you know, limbs that can bend more convincingly, or something advanced like this. There are many use cases for mesh deformation, but obviously not every armature is going to require it. And also, speaking about runtimes, not every runtime will support mesh deformation. As of making this video, Pygame is the only runtime that doesn't support it. So if you're making a game in Pygame, and if you're making these armatures for Pygame, you do have to keep in mind that. And you will also have to make sure that you just use simple textures, you don't use any meshes. Inverse kinematics is supported though, so you can continue using that, but just keep in mind that meshes might sometimes not be supported in the game engine or the runtime that you want to use it for. That will be all for this tutorial. We've gone over everything that mesh deformation has to offer, like vertices, triangles, binds, weights, pathing, and so on. In the next tutorial, we will go over the basic physics that SkelForm has to offer, such as damping, swaying, and bouncing. If you have any questions about mesh deformation or SkelForm in general, feel free to join the Discord server or the forums. See you next time!